All right, welcome to use case 9. So, this is a celebratory video. We're celebrating because it's the final use case. We can see I'm uh, already more than 3/4 of the way done with the book. And in fact, we've only got 90 more pages to read. So, let's waste no time and get into use case 9. Let's generate some new fake logs. Pain point. The pain point we're going to focus on in this use case is not likely something you face on a daily basis, particularly in the context of a network operation. However, both development and network operation software and testing and validation of such software requires data that can be used to provide validity and correctness of the rules and or algorithms. SANS itself is a good example of a system developed to alleviate that pain by simulating a network environment and generating data using predefined templates. Lack of sufficiently realistic data makes it very hard to validate implementations, which ultimately results in longer times to bring new solutions to market. Therefore, the pain point we are trying to alleviate is the difficult access to realistic data in lab environments to validate operational software rules and algorithms. Approach. Given that we have been using logs in the last couple of use cases, we will continue in this one to finalize the mini block of use cases with logs and NLP. We have reviewed in the theory that there are two main categories of algorithms: discriminative and generative. In a nutshell, discriminative algorithms try to learn about the boundaries between classes to classify correctly. Generative algorithms try to learn about the class's distributions and understand the rules that govern the data generation within those classes. As a byproduct, generative can also be used to do classification. Over the past years, there have been very significant breakthroughs in the space of generative algorithms, with jaw dropping results in the context of fake images, video, and audio generation. Architectures such as GAN, generative adversarial networks, have enabled a good portion of these outcomes, but other recent developments, such as stable diffusion, are now taking the lead. Since the primary goal of these use cases is to help you understand machine learning by doing, we will use the pain point above to demonstrate how we can build and use a GAN, generative adversarial network, to generate fake and realistic logs. The hypothesis here is that if GANs are used to generate realistic images or videos, why not give it a try and evaluate if they can also be used to generate realistic log messages? We could potentially use those fake log messages in our lab environments. I want to highlight that this is quite a complex use case, more complex than all the previous ones. GANs are complex structures to define and train. I will try to make the description as easy as possible, going through every step in the process. GANs are somewhat unstable architectures that are not guaranteed to converge. In our case, it does converge reasonably well, but only after many different tests with various network architectures which never converged. But this is part of the process, trial and error. The approach described in this use case is based on existing public research. See 3.4 for reference. Input data. We will use the same logs we used in the previous use case, so I will not elaborate on the description again. The only difference is that we have the logs now loaded in a different text file. Previously, we had saved in a CSV file the contents of a data frame. Now we are only interested in the logs, so we will have a text log called logmessages.txt, which simply has logs in it, one per line. You can generate new logs and write them in logmessages.txt file, or simply use the existing file. There is a difference, though, with the previous examples where I was loading the file and then doing transformations. I will be building, in this case, a set of functions to build a pipeline of transformation as we load the file. Problem resolution. The resolution is built in two parts. Part 1, autoencoder. Part 2, log generation with GAN, Generative Adversarial Network. Let me explain the rationale of this. The following diagram is the structure of GAN we want to build. Okay, so here's a diagram. What I've been doing with these is just pasting these into ChatGPT and seeing what it has to say.
This diagram represents the architecture of a generative adversarial network, GAN, tailored for log data. Here's a brief explanation of its components. Generator. The generator takes in some noise and generates fake log data. Discriminator. The discriminator receives both real log data and fake log data from the generator. It outputs a decision indicating whether the log data it received is real or fake. Real logs. This is the source of the genuine log data that the discriminator uses to learn what real data looks like. Fake log. This is the output from the generator that the discriminator uses to distinguish from real data. Feedback loops. The discriminator provides feedback in its decisions for both real and fake data to improve the generator in itself. The process involves training both the generator and the discriminator in tandem. The generator aims to produce log data that is indistinguishable from real log data, while the discriminator aims to improve its accuracy in distinguishing between real and fake log data. This iterative training continues until the generator produces high-quality fake logs that the discriminator can no longer reliably distinguish from real logs. If you need further analysis or a different kind of assistance with this diagram, please let me know.
Alright, so that's it. Moving on. If we succeed, the generator will learn how to generate realistic fake logs, while it has never seen a log itself. That is the magic of a GAN. There is one problem with the use of GANs to generate text, though. As you already know, the machine learning models do not deal with text. They deal with numbers. So when we work with text, we transform it to numbers and then back to text. So far, so good, but the way to represent text in numbers is usually one hot encoded vectors, zeros and ones. The discriminator would need to receive zeros and ones. So is what the generator would need to produce. But models never generate zeros or ones. They generate probabilities, real numbers between 0 and 1, or simply real numbers. And then we do some interpretation of them, which transforms them into zeros or ones. For example, set a threshold at 0.5, or pick up the maximum value of a vector and set this one to 1. These functions of interpretation work well for the human consumption of the output, but they do not work well inside a model because they are not differentiable. For example, they do not have derivative. Why is this relevant? The training of a neural network is based on the concept of gradient descent and backpropagation. This assumes all the functions along the path are differentiable. Another option is why the generator cannot generate those perfect zeros and ones. It is extremely unlikely it could do that. This is the reason why we need a bit of a different strategy. Here is where the autoencoders come to our rescue. If you remember, autoencoders transform the input data, our zeros and ones, into a new space, the latent space, which is a n-dimensional space of real numbers. In this space, we have a vector of real numbers that legitimately represents a log. That gives the possibility to run the GAN with data in the latent space. Transform real logs into the latent space using the encoder part, and then transform the fake logs from the latent space into the zeros and ones space just at the end of the process for us to visualize the results. However, every other operation is strictly in the latent space in real numbers. That is the reason why in the first part we will train an autoencoder that will enable us to use a GAN as a subsequent step. The following diagram shows the target architecture. So tried and true into ChatGPT to get an explanation.
The second diagram adds additional components to the generative adversarial network GAN architecture by incorporating encoders and decoders, likely transforming it into a type of variational autoencoder GAN, VAE GAN. Here's a breakdown of the components and their roles. Encoder transforms real log data into a latent space representation. Decoder converts the latent space representation back into log data. Also used to decode fake log data generated by the generator from latent space. Latent space, a compressed representation of log data, where both real and fake data can be compared more effectively. Generator takes noise as input and generates fake log data in latent space. Discriminator receives both real and fake log data in latent space. Provides feedback on whether the data is real or fake, contributing to the training of both the generator and itself. Real logs, the source of genuine log data which is encoded into latent space before being fed into the discriminator. Fake log in latent space, generated by the generator. This fake log data in latent space is decoded back into log data. Feedback loops. The discriminator gives feedback on the authenticity of the data for both real and fake data, improving both the generator and the discriminator. The decoder also helps in reconstructing the data from latent space back into log format for further evaluation. Process flow. Real logs are encoded into latent space. Fake logs are generated from noise in latent space by the generator. Both real and fake logs in latent space are fed into the discriminator. The discriminator provides feedback on their authenticity. The decoder reconstructs fake logs from latent space back into the original log format for final output. This architecture allows for more nuanced generation and discrimination of log data by working in the latent space, potentially improving the quality and realism of the generated log data. If you have any specific questions or need further analysis on this architecture, feel free to ask.
Oh, so it looks like there is actually a use case 10. There's just no notebook for it. So unfortunately, this isn't the last use case. There's just no... Oh, there is a notebook for it. Well, where is the notebook then? Okay. Anyways, eyes on the prize. Yeah, so the dotted lines represent only the fact that we have taken either the encoder or the decoder and placed it in a new position, leveraging exactly the same weights and architecture used to train the autoencoder. As you can see, things have gotten a bit more convoluted in this use case, but let's do it one step at a time. We need to start, therefore, by our autoencoder, which is a fundamental piece of this puzzle. We will need the autoencoder to be as good as possible because its ability to transform a log into the latent space and then transform it back to the same structure is very important for overall success. Okay, so the author's introducing a new concept there. I'm kind of was over ambitious in doing a second video this morning. So I feel like this is a good place to stop. Yeah, I was just over ambitious. I don't have the energy to keep going. So this is going to be a good stopping point. So thanks for watching just this short one here, and stay tuned for more.